Hey again, it's Mr. Lum, and we're going to continue our acid-base chemistry unit and talk about pH and pOH scales. Okay, so the pH and pOH scales are based on what is called a logarithmic scale. Okay, now many different ways of measuring things are based on logarithmic scales. For example, earthquakes. Earthquakes are based on a logarithmic scale, or in other words, the Richter scale. So you may have heard of like an earthquake with a rating on the Richter scale of, say, 4, and another earthquake with a rating 5. Okay, so what is the difference between 4 and 5? We know that 5 is a bigger earthquake than a level 4 earthquake, but how much bigger is it? How much more power does a Richter scale with a 5, how much more is it than something with a 4? Well, that's the interesting thing about logarithms, is that well, on many logarithmic scales they have what is called a base 10. So the difference between 4 and 5 is that 4 and 5, a 5 is 10 times more powerful than a 4 is. And same thing if we have a 6. A 6 is 10 times more powerful than a 5. Now what's the difference between a 4 and a 6? Well, it's actually 10 times 10. So a 6 is 100 times more powerful than a 4 earthquake. Okay, and we use pH scales and pOH scales the same way as the Richter scale. It's on a base 10 thing. So let's talk about pH and pOH, and what does it mean? Well, all it means is that the concentration of H plus on a logarithmic scale, or P. So the P is like a German kind of word that kind of means potency, or in other words, how strong it is. So the concentration of H on a logarithmic scale, and we just put a P in front of it, and pOH is the concentration of OH on a logarithmic scale. And so therefore, since it's just a logarithmic scale, we can convert between concentration of H plus and OH minus quite easily. So H3O plus, or in other words H plus, and just put that, the negative log of H plus equals pH, and the negative log of OH minus equals pOH. And we'll talk a little bit about this one a little bit more. But at 25 degrees, pH plus pOH equals 14. So let's take a look at what we now know. Okay, if we know H3O plus, we can change this quite easily to OH minus. Okay, and if you remember in a previous video, how do we do that? Well, we can change it from H0 plus to OH minus using our KW formula. So we can use KW, and we know that KW equals H3O plus times OH minus. So this is no problem for us to use this formula to go back and forth here. We also now know how to go from H3O plus into pH. We can use this formula right here, which is pH equals the negative log of H3O plus. Okay, and same thing with this one. We know that pOH equals the negative log of OH minus, and that will make our potency of OH, or in other words, our putting our concentration of OH on a logarithmic scale, pOH. And now we can go, using this formula, we can transfer between and connect these two ideas. Okay, using this formula, pH plus pOH equals 14. And later on we can derive this formula using this formula right here. Okay? Now, here's the question, is that how do I change pH back into H3O plus? Like, I have this formula that, you know, if I take the concentration of H3O plus and put it on a log, how do I take it back and make it back into the concentration of this if I just have pH? So we can just kind of do a little bit of math right here and look at how pH equals the negative log of H3O plus. Now, if we times both sides by -1, it becomes the negative pH equals the log of H3O plus. Now, if I were to take, this is the log, so if I were to take the anti-log, okay, of both sides, then that would equal H3O plus. So, what is the anti-log? As I mentioned before, a logarithmic scale like pH or POH or the Richter scale is what we call a base 10. Okay, it's the most common type of base for a logarithmic scale. Technically, you can have a base of anything you want, but pH is always done on a base 10. So, and again, we talked about how 4 and the difference between 4 and 5 is 10 times stronger. Okay, so what it is if we take the anti-log, all it is just putting this 10 to the power of negative pH. And if we did this to this side, it's just going to cancel out this log right here, and then you're just left with H3O plus. Okay, so if you want to take pH and change it back into H3O plus, all you do is take 10 to the negative pH, which equals H3O plus, or this is just sometimes called anti-log. Okay, and same thing with this one right here. It'd be 10 to the negative POH. This equals concentration of OH minus. Okay, so what is this anti-log, and where do I find it on my calculator? And even so, what is log, and where do I find it on my calculator? So let's take a look at that. So hopefully you have a good scientific calculator like one of these ones, and you see you can easily quite find hopefully the log buttons right here. They're in very similar places. And the anti-log, if you have like a sharp calculator, you'll have to hit second function and then log, or you see 10 to the x, which is like the anti-log, or you have to hit on a Casio. It looks like 10 and then it shows like this little picture of a square right there. Okay, so you have to look for those on your calculator, and that is so you have to shift first and then this one, and that's your anti-log. So again, I mentioned how pH is on this base 10 scale, and let's take a look at a few different things. So let's take a look at a neutral solution. Okay, so in other words, it's where the concentration of H3O plus equals 1.0 times 10 to the minus 7th molarity. Okay, if we take this, we plug it into our formula right here to find out what the pH is, you'll find that the pH for this equals 7. Okay, and what that means is that, well, we know that this is neutral, and we know that pH is, when the pH is 7, we know that that is also neutral. Okay, now what we're going to do is we're going to take this and we're going to increase it by 10 times. We're going to essentially multiply this number by 10, make it 10 times more acidic. So we're going to increase this concentration by 10 and go 1.0 times 10 to the minus 6. Okay, and that is going to give us a pH of 6. Okay, if you put it into this formula right here. And you can see that it kind of stays true if, again, you multiply it by 10. pH equals 5. So again, what's the difference between 7 and 6? Well, 6 is 10 times, has 10 times the concentration that 7 does. And the difference between 7 and 5? Well, 5 has 10 times 10, or in other words, 100 times the concentration that 7 does right here. And same thing for pOH. pOH. So if we had a concentration of OH minus that was neutral, or in other words 1.0 times 10 to the minus 7, we'd plug it into this formula right here, and we'd see that this equals 7. Now if we increased this by 10, okay, we would find that it goes like this. So again, pH and pOH scales, they're very, very much related. However, the lower the number it is for pOH, the more basic it is, and the lower the number it is for pH, the more acidic it is. Now let's take a look at a few questions. Okay, here's our first question. It says, what is the pH of when you have a concentration of OH that equals something like this, 7.53 times 10 to the minus 3. So what we're going to do is we are going to take OH here, the concentration of OH, and well, we know that Kw equals the concentration of H3O plus times OH minus. Okay, and I'm going to plug in a few numbers here. So you know Kw is 1.00 times 10 to the minus 14th. Okay, we don't know what H3O plus is, but that's our variable that we're looking for, our unknown, sorry. And OH minus, well, that is 7.53 times 10 to the minus 3. We're going to rearrange this to solve for H3O plus. So H3O plus equals 1.00 times 10 to the minus 14 divided by 7.53 times 10 to the minus 3. Okay. Now we're going to, if you remember what our pH formula is, pH equals the negative log of H3O plus. Well, this is what H3O plus is going to equal. So we're just going to take this number and plug it into right there. Okay, so in other words, our pH equals negative log of our water constant and if we plug this into our scientific calculator right there, we find that pH equals 11.8768. Okay, so now first thing we should do is, does this number make sense? And we see here 7.53 times 10 to the minus 3 is the concentration of OH. In other words, this number is bigger than 1.0 times 10 to the minus 7. Okay, so since it's the concentration of OH is bigger than that, we know that it should be a basic solution, right? And pH with a number that is bigger than 7, oops, this should be 11. If we know a number that is bigger than 7, we know that this is a basic solution. Okay, good. Now, we do have to do a few different things on this one first. So this, but first, this number does make sense, so it seems correct. Now the next thing is sig figs. Okay, now this is 3 sig figs and this is 3 sig figs. So 1.00 and 7.53, they're both 3 sig figs. So we have to convert this to 3 sig figs. The interesting thing about logarithms is that you only count significant figures after this decimal place. You don't really need to know this, but the reason why is because this number, 1.00 times 10 to the minus 14th, this has 3 sig figs. This one, and this one. This times 10 to the minus 14 is not significant. And this times 10 to the minus 3 is not significant. There's only these 3 are significant. Okay? Now what we're doing is we're putting on a logarithmic scale, and so this number kind of over here is converted into these larger numbers right here. So when we don't count these numbers as significant figures. We only count after the decimal place as significant figures. So again, we have 3 sig figs here, 3 sig figs here, so this answer needs to be 3 sig figs. So our answer is pH equals 11.877. Okay, again, this looks like it's 5 significant figures, but it's only 3. Only count after the decimal place. So there's only these 3 are the only ones that are significant. Okay, so this is 3 sig figs. I know it looks like 5, but it's only 3 sig figs. Okay, and this is our final answer. pH equals 11.877. Okay, let's try working on this next one right here. What is the concentration of OH minus in a solution with a pH of 4.53? So there's 2 different ways we can solve this question. The first way we can solve it is, well, we can solve it by taking this concentration of, or this pH and changing it into POH, okay, and then changing POH into concentration of OH minus. That's one way we can do it. Or the other way we can do it is take pH, change it into H plus ions, and then use our kW to find the concentration of OH. And let's try the latter one. Okay, so we're going to take pH and we're going to go 10 to the minus pH equals the concentration of H3O plus. Okay, so, or in other words, 10 to the minus 4.53 equals H3O plus, or in other words, H3O plus equals, and I came up with 2.95 times 10 to the minus 5. Okay, and then now I'm going to use my kW formula. Okay, and kW equals H3O plus times OH minus. Okay, or in other words, it's going to be 1.00 times 10 to the minus 14th. Okay, equals 2.95 times 10 to the minus 5. That's OH minus. Solve for OH minus, and we see that is OH minus equals and we see it's 1.00 times 10 to the minus 14 divided by 2.95 times 10 to the minus 5 right here. Okay? And if we do this calculation, what we're going to see is that our concentration of OH equals 3.38 0.98 times 10 to the minus 10. And this has a concentration, so it's a molarity. So what we now let's so here's our answer. Now let's go back and just make sure we have all the correct significant figures. So what we see here is that we have pH that is 4.53. Now how many sig figs is that? Again, you only count sig figs when it's on a logarithmic scale after the decimal place. So this has 1 sig fig, 2 sig figs. I know again it looks like it has 3 sig figs, but it has 2 sig figs. The 5 and the 3 are the significant figures. Okay. Now let's put it back into this kind of value right here. So if this is if this pH is 2 sig figs, then this is also has to be 2 sig figs. Okay, and so we're looking at 3 sig figs divided by 2 sig figs. Our final concentration of OH needs to be 2 significant figures. Okay. So 2 sig figs, that's going to be 3.4 times 10 to the minus 10. Okay. Now this is significant and this is significant because this concentration of OH is not on a logarithmic scale. So this is 2 sig figs. Okay, and that is our final answer. Okay, 2 sig figs. I know this one is before the decimal place right here, but again, it is not on a logarithmic scale, so we count it. This is 2 sig figs, and this is 2 sig figs. Okay, we do not count this times 10 to the minus 10 right here. Okay, this is not part of our significant figures calculation. Okay.